All right. So once we've done indefinite integrals, right, essentially just finding antiderivatives, um, what comes next is what we call the fundamental theorem of calculus. And this has to do with what we call the definite integral. So I'll put some words here, and then we'll sort of talk about the concepts. So this is just my wording. Should I have picked wording from the book? Well, I don't know, maybe. These are my words. So if capital F of x is an antiderivative of sort of regular f of x, lowercase f of x, then the area under the curve of little f of x on the interval a to b, the closed interval a to b, is given by this, right? So this is the integral from a to b. So this is the definite integral, right, of the function, right, little f of x, sort of normal f of x, with respect to x dx. And then what this is equal to is capital F of x, right, which is the antiderivative. So aka what we've been doing, right, finding the antiderivative when we integrate. So it's that function evaluated at b, right, the upper value here, minus the antiderivative evaluated at a, which is the lower value here. It's always going to be the upper minus the lower based on what's here on the integral. You can sort of mess around with things a little bit. You can kind of flip the order here, and what that would do is it would flip the order here, and it would give you a negative value where you would get a positive, or sort of vice versa. It will just sort of flip this subtraction and then give you the opposite signed value of what you would expect. But this is what we call the fundamental theorem of calculus. So this is extremely important. It gives us what we call the area under the curve. So in the same way that derivatives, right, if you sort of find a derivative function and then you kind of evaluate it, what you're finding is the slope of the tangent line at that point. You're finding the sort of instantaneous rate of change. What you're doing when you sort of integrate over an interval is you're finding the area under the curve. We'll kind of get into more details about what maybe that could mean in sort of different contexts. You guys have done sort of Riemann sums and sort of talked about area. Generically, right, the idea that you're kind of adding up all these individual kind of rectangles to kind of get an area under the curve, those concepts are there. The picture that we get, so I have an example and I sort of have a sketch that goes with it, right? So we'll just pick a nice, essentially as straightforward an example as we possibly could get. And that would be something, the integral from 1 to 2, right? Positive 1 to positive 2 of x squared, the function, with respect to x. Always, of course, right, keeping in mind we want the variable here to kind of match with the variable here. Okay, so what does that give us? Well, it gives us a picture of x squared, right? So we have our sort of poorly drawn version of our sort of standard parabola. And what this is giving us is the area under the curve. What that means really is the area between the curve and the x-axis, right? So area under the curve means whatever the sort of region is that would be between the curve and the axis, the x-axis. And so we're doing that from x equals 1 to x equals 2, right? So over the interval 1 to 2, we're getting this, trapezoid-ish kind of shape. It has this sort of curved value here, so it's obviously not an actual trapezoid. So part of the idea here, right, is this is a way to find areas of shapes that wouldn't just be our standard geometric shapes, circles, rectangles, triangles, trapezoids, that kind of stuff, right? This gives us a way to sort of find areas where we have different shaped curves along the edges. So what is the actual area here? What is the actual calculus of this going to look like? So what the fundamental theorem says is we need the antiderivative, right? We need this capital F. It's just the antiderivative, the same antiderivative that we've been finding. I have just x squared here, so my antiderivative is going to be, right, 2 plus 1 is 3, divide by 3. And how I'm going to notate this, right? So that's the antiderivative. I'm actually going to leave the plus c off of it. If we think about having a plus big C as a generic constant on the end. You know, if this is big F plus C and this is big F plus C, and we're subtracting them from each other, the C values are going to get canceled out. So we don't really need that generic coefficient. It's literally going to get canceled out in this process, so it doesn't have an impact. So I'm going to leave it off here, and what I like to do to sort of notate this is I'll mark a bar here, and then I'll put those boundaries on. So this is my antiderivative, so I'm dropping the dx, right? I'm dropping the integral. I'm sort of bringing a bar over here. I'm sort of straightening it, just using a straight bar. Sometimes you'll see maybe a little bit of a bracket kind of thing, and I'm putting those boundaries on. And so all I'm going to do is I'm going to take those two boundary points, 2 and 1. I'm going to sub them in here, and I'm going to subtract the top minus the bottom. So this is going to look like, right, just regular function substitution kind of stuff. You know, the antiderivative evaluated at 2 and evaluated at 1. Parentheses are big here. So I would do, right, 2 cubed over 3 minus, right, 1 cubed over 3. I would write it like that, right? So this is x cubed evaluated at 2, right? Big F of 2 minus, right, big F at 1, right? 2 goes in, 1 goes in. Same format, right? And again, I like having a lot of parentheses here so we keep track of everything. This is a subtraction, so of course when we do that, having those parentheses helps to keep everything organized. You know, a common mistake that will of course screw up your answers and be very frustrating is messing up in these parentheses and you know, not carrying this negative to each of the terms in your sort of second example. We'll sort of see that in some of these ones coming up. In any event, so what are we going to get here? This is 8 over 3 minus, of course, this would just be 1 over 3. So the value here is 7/3. What does that mean? So that means the area here, so the area of this shape, right, which is sort of a semi-irregular kind of shape, right? It's not distinctly a trapezoid or something like that. It's going to be 7/3, right? So that's, you know, 2 and 1/3, and that's what we found. Let me shift this up. This is not going quite the way I want. Let me shift this up. If we do a second example, I have another example here with a little bit of a different picture, but the same kind of concept. And one of the things that happens here, I'll try to see, yeah, I think that's pretty visible. So if I adjust this function just a little bit, let's do x squared minus 1 instead of just regular x squared. So it's still our standard parabola, but everything is shifted down by 1. So now it dips underneath the axis between -1 and 1. What happens here, if I sort of look at the interval now from 0 to 2, what I'm going to get is a piece that's under the axis and a piece that's above it. And what happens here conceptually is any region that's under the axis counts as negative area. So this sort of small, you know, triangle-ish kind of thing, but right with a curve, I guess they both are sort of triangle-ish, you know, they're triangle, yeah, ish. I guess triangle-ish is the best thing to say. Let me see if I can say that anymore. So we have a negative chunk down here, and then just to look at it, to eyeball it, I mean, of course, this is my not wonderful drawing, but it looks like this positive portion is bigger. So probably the overall area is going to be positive here. But one of the things that can happen when we're doing this, you know, if we did this and found the area under the curve, of something that was mostly underneath the axis, you would actually end up with a negative area. So this is sort of area in the sense of sort of on the XY plane, where you could have, you know, if you think of this in terms of lengths, you know, width times, you know, base times width or something, right? Length times width, as far as getting an area, you know, anything that's sort of underneath or anything that's kind of back here could have a negative value, right? So this is sort of, if this is like your height and this is your width, your kind of height here is negative, so that chunk of area comes out negative. In any event, the nice thing here, we don't need to do anything wild where we're trying to break this up and say, okay, so from 0 to 1 it's negative, and from 1 to 2 it's positive. The amazing thing here is if I just do the same thing I did in the last one, everything comes out in the end. I don't even really need to worry about it. So I'm spending whatever 5 minutes talking about this when I could essentially just sort of wave my hands and be like, but don't worry about that. Now, antiderivative here. So x squared, of course, we just did goes to x cubed over 3. 1, right? Now that has its own antiderivative, right? It goes backwards to x. And so then this is going from 2 to 0, or from 0 to 2, right? So my antiderivative here has two pieces. That means when I sort of set this up and I set up the subtractions, the parentheses become sort of even more important because I have to subtract, right? This whole thing is my big F. And so I got to sub in big F at 2. So 2 cubed over 3 minus, going in here, minus 2. And then that whole thing we're going to subtract, big F at 0, 0 cubed over 3 minus 0. So a couple things happen here that are nice. We need to make sure we don't take it for granted, but the second value here is 0. If I sub that in here, right, 0 cubed over 3, 0, minus 0 is 0. Everything here is 0. It's just a bunch of zeros, right? So that second piece just totally gets wiped out. This would, of course, be what? This is our 8/3 again. You know, minus 2 minus 0. 8/3. 2 would be 6/3. So this ends up being 2/3 in the end. Different shapes, obviously, right, we're definitely dealing with a different shape than we did in the last one. We get a very different answer. We're getting an area here that's less than 1 relative to the previous example, which was, right, 7/3 is sort of 2 1/3. So the negative area here is cutting into this, even though it looks like that probably would be smaller anyway. The negative value here is sort of cutting into it also, and has an impact. So that's kind of getting started with these definite integrals using the fundamental theorem. And so there's always this visual that goes along with it. You're not always going to have to sort of sketch these graphs necessarily and sort of sketch these pictures, but that's a concept that should kind of always be sitting in the back of your head. And we're going to be using that picture, right? Using that concept to extend on it in further chapters. We're going to be able to sort of leverage that kind of concept and that idea to be able to sort of find areas between two curves, or even extend it out to being able to do different types of volumes. It's also the kind of thing, if you do any sort of physics and you end up using calculus in physics, part of your integration there, you can sort of use it to find different things. What would kind of be the area under a curve in physics, right? If you sort of find that area and it ends up being sort of two dimensions multiplied together, depending on what your things are, you're likely to get all sorts of stuff. In any event, that's a story for another day. We're going to do one last fundamental theorem, right? Definite integral video. I just want to run a few more examples without the sketches, just sort of run a couple more integrals and include the boundaries on there just for some more practice. So we'll have one more video here for this review, and that'll be that.